Hello and welcome back to the course on machine learning. Today we're talking about support vector machines, or SVMs for short. So SVMs were initially developed in the 1960s, then they were refined again in the 1990s, and only now they're becoming very popular in machine learning because they are demonstrating that they can be very, very powerful because they are somewhat different to other machine learning algorithms. And we'll find out how they're special towards the end of this tutorial. But for now, let's understand how support vector machines actually work. All right, so here we've got, as usual, points on a two-dimensional space. For simplicity's sake, we've got just two columns, x1 and x2, and we've got some observations. Some are red, some are green. So we've already classified them. But now, how do we derive a line that's going to separate them? So how do we actually separate these points? Because that separation, or in other words, that decision boundary is going to be very important for us going forward when we start adding new points. So that's the point of our classification. That's the purpose of our classification. We want to create a boundary between these two so that when we in the future add new points that we want to classify that haven't been classified yet, we will know where they will fall, either in the green area or in the red area. So how can we separate these points we see here? Well, one way is to draw a line like that in our two-dimensional space, and then so anything to the right will be green, anything to the left will be red, and if a new point falls somewhere on this space, we will know right away if it's red or green because we'll know where it falls. However, there's another way. We can draw a horizontal line like that, or we can draw a diagonal line like that. We can actually draw another diagonal line, or we can draw another diagonal line. So there's lots of different lines that we can create that will achieve the same result. They'll separate our points into two classes, but at the same time, they all in the future will have different consequences. So when we add new points, depending on where that point will fall, it'll either be classed as part of the green zone or part of the red zone. So we want to find the optimal line. And that's what SVMs are all about. They're about finding the best line or the best decision boundary, which will help us separate our space into classes. So let's find out how the SVM actually searches for this line. Well, the line is searched through the maximum margin. So here you can see a line, and this is the line an SVM would draw. And so basically, it's the line that separates these two classes of points, and at the same time, it has the maximum margin, which means this distance. So this line is drawn equidistant from this point and this point, and we'll find out exactly why these points in a second. And then the distance between the line and each one of these points, so that's equidistant. And that margin, so the sum of these two distances, has to be maximized in order for this line to be the result of the SVM. And these 2 points are actually called the support vectors. Why they're called vectors, we'll also find out in a second. But so basically, these 2 points are supporting this whole algorithm. So even if you get rid of all the rest of the points, nothing will change. The algorithm will be exactly the same. So these other points, they don't contribute to the result of the algorithm. Only these 2 points are contributing, and therefore they're called the supporting vectors. You can call them supporting points, but in reality they're vectors, and this is why. Because in a multi-dimensional space, when you have more than just 2 variables, you can have 3, 5, 10, 100 variables. Each point is actually no longer a point because you can't visualize it on a 2-dimensional plane or even a 3-dimensional space, and therefore each of those points that we see here is actually a vector in a multi-dimensional space. So the more general term for points that we see here are vectors, and this is something that is studied in mathematics in university or high school mathematics. And basically, so generally speaking, they're all vectors. Just in this particular example, when we have 2 dimensions, then we can call them points. But in reality, they're vectors, and that's why they're called support vectors. So hence, these 2 specific vectors are the ones supporting this decision boundary, or this way we're building this algorithm. That's why they're important. That's why this whole algorithm is called the support vector machine. So now, what else do we have here? Well, we've got the line in the middle, which is called the maximum margin hyperplane, or the maximum margin classifier. So in a 2-dimensional space, it's just like a classifier, it's just a line, but actually in a multi-dimensional space, it's a hyperplane. And I know it's a very a bit of a confusing term, but that's what it's called, a maximum margin hyperplane. So those all other ones that we saw were also hyperplanes, but they weren't the maximum margin hyperplanes. And you can check that yourself. So you can draw a different hyperplane here and just check what the margin will be. It'll always be less because this is the one with the maximum margin. And then you've got the green and the red dotted lines. So the green one is called the positive hyperplane and the red one's called the negative hyperplane. It doesn't really matter in which order you name them, just the point is that one of them is positive, the other one is negative. Basically anything to the right of the positive is classified as the green category or the positive category. Anything to the left is classified as a negative category or the red category in our case. So that's how the support vector machine algorithm works. Of course, there's some complicated mathematics behind it, but the essence, the intuitive part of it is exactly this, that we're working with a linearly separable data set where we can actually, it's given to us by default that we can put a line through our chart which will separate the two categories, and then we're just searching for the one with the maximum margin. So conceptually, when you think about it, it's actually a pretty simple algorithm when you think about it this way, without going into the mathematics. And the question is, what's so special about SVMs? Why are they so popular and why are they different to other machine learning algorithms? And that's exactly what we're going to talk about right now. So imagine you're trying to teach a machine how to distinguish between apples and oranges, how to classify a fruit into either an apple and orange. So you're telling the machine that, all right, I'm going to give you some test data. So have a look at all of these apples. These are apples, these are oranges. Analyze them, look at them, see what parameters they have, and then next I'm going to give you a fruit which will be either an apple and orange, and you're going to need to classify it and tell me whether it's an apple and orange, right? So that's kind of a standard machine learning problem. Now in our case here you can see, let's say on the right we have oranges, on the left we have apples. So what predominantly machine algorithms would do is they would look at the most appley apples and the most orangey oranges. So they would look at the most stock standard common type of apples and the most stock standard common type of oranges. And in our case it'd be apples somewhere over there in the very heart of the apple class, far away from the oranges. And for the oranges would be somewhere over there. So also in the very heart of the orange class, far away from the apple. So a machine would try to learn from the apples that are very like apples, so it would know what an apple is, and it would also try to learn from oranges, so it would know what an orange actually is. And that's how most of the machine learning algorithms work. And then based on that, it would be able to come up with some predictions and classifying for new data elements and new variables that you would give it. In the case of support vector machine, it's a bit different. Instead of looking at the most stock standard apples and stock standard oranges, what the support vector machines do is they actually look at the apples that are very much like an orange. So here you can see an apple which is not your standard apple, it's orange in color, right? So it's very easy to confuse this apple with an orange. And they would look at oranges which are not stock standard oranges, which are more like apples than anything else. So ignore the lemon here, it's not supposed to be in the image. Just out of the oranges, the SVM would pick the one that looks the most like an apple. In this case, we have a green orange. It's not normal to have a green orange. When you think of orange, you think of orange. And so what that is those are the support vectors. So the support vectors, you can see that they're actually very close to the boundary. So they're very close to the apple, or the red one would be very close to the green ones, and the orange or the green mark here would be very close to the red ones. And therefore, the support vector machine, in that sense, you can think of it as like a more extreme type of algorithm, a very rebellious type of algorithm, a very risky type of algorithm, because it looks at the very extreme case, which is very close to the boundary, and it uses that to construct its analysis. And that in itself makes the support vector machine algorithms very special, very different to most of the other machine learning algorithms. And that's why at times they perform much better than non-support vector machine algorithms. So there you go. I hope this explanation and intuition of support vector machines was useful. And now not only you know how they work, but also why they are different to other algorithms out there that are used in machine learning. And on that note, we're going to end today's tutorial. I look forward to seeing you next time. Until then, enjoy machine learning.